Chapter 12, Liquid Solids and Intermolecular Forces. Kind of an unlikely quote here from Roald Hoffmann. It's a wild dance floor there at the molecular level. I'm going to watch this video about water in zero gravity. It's the Canadian Space Administration.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung-out cloth? So, and had to use equipment that was here on board the space station. We might have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's packed it. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Merritt and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it.
She just said bags
And I'm
don't
going
hold water.
to squirt a bunch of water into this
She meant
washcloth.
open bags.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet.
Isn't that interesting?
That is so cool. So it's like keeping it together. It's not pulling apart. The bonds aren't pulling apart, right?
Yeah, so it's not falling in drops like it does when there's gravity.
The water's all over my hands. In fact, it rings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands.
Interesting.
And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations. Great idea.
Have you ever seen the movie Life?
Yes.
That's the it reminds me of water. Oh, so that's the guy that we just saw?
Yeah.
Oh.
Yeah, it's interesting because I saw this picture, this is a picture from the textbook, and I'm like, oh, that'd be really cool if we could get a video of water in space. And it turns out it was the same guy. So perfect. Make sure I didn't skip anything. Okay. So he mentioned surface tension, right? Why did the water do that? Why did it just slide along his hands instead of falling in droplets off of the washcloth? Well, we're going to learn about that today. And it has to do with intermolecular forces. So these are attractive forces that exist between all molecules and atoms. They are significant only at very short distances. They are responsible for the very existence of liquids and solids, and they are essential for physiological processes. So, intermolecular forces play a big part in biology and biochemistry. Very important. So, the state of a sample of matter, whether it's solid, liquid, or a gas at a given temperature, is going to depend on how strong the intermolecular forces are relative to the amount of thermal energy. And the amount of thermal energy is going to depend on the temperature. So it's these intermolecular forces that were holding those water molecules together instead of letting them split apart. The reason water doesn't do that on Earth is because gravity is pulling on it. When you squeeze it out of the rag, gravity is pulling down, and so it will fall off in droplets. But the reason that it forms drops is because of the intermolecular forces.